So this is a 10-year retrospective on what it was like operating Ceph at CERN. So quick for those that don't know me, that's my email addresses. I'm a Canadian guy. I'm from University of Victoria. I've been on the engineering staff at CERN since 2008. I was managing Ceph there until last year, and then I handed off the reins because I became chief IT architect at CERN. That's one hat. Other hat is I've been happily supporting the Ceph Foundation and being a founding board member, and now honored to be on the Ceph Executive Council since 2021, when our benevolent dictator for life moved on to greener pastures. And then actually, latest news is in April, I'm relocating to Vancouver, and I'll be taking a sabbatical from CERN. I'm going to be joining Joachim and company to help build up Clyso in North America. So that's me. What's that cool picture behind? That's the LHC at CERN. Large Hadron Collider, 27-kilometer ring. This is where I work these days still. 100 meters underground. My house is like right there, somewhere right there. That's my house. There's a ski hill going up. When it gets cooking a little bit, it melts the snow a little bit. Not too much, but this is what it's like 100 meters down. That's the superconducting accelerated magnets. They accelerate protons up to the speed of light minus 11 kilometers per hour. Just hit the brakes a little bit. They bend those opposing beams together at four corners of that circle, collide them like psh, and then take pictures in giant cameras like this. So you can see someone that may or may not be me standing there to get the idea of how big that camera is, how big that camera is. And then it takes pictures like this. This is a picture of the Higgs boson. This is the whole reason that we built the LHC at CERN. And this is the particle. This is not the particle. This is like the splash after that particle was created and then decayed very quickly. And that's the thing that gives everything mass. And that's why we weigh something. Yeah. So actually, yeah, it's really crazy. I'm a computer guy, but somehow I got my name on the paper that discovered the Higgs boson for Atlas, and which then got a Nobel Prize. Okay, I don't have the prize. Someone else got it, but this is cool. Like, how can you get a highlight of your career beyond that? Anyway, okay, 10-year retrospective. You know, I'm moving around. I'm kind of a busy guy. How do you outline a 10-year retrospective? What would one do these days? One would ask a certain intelligent system, what should be, oh, that's unfortunate, the text is right there. Write an outline for a 10-year retrospective. Sure, here's an outline. This is my Ceph GPT bot, okay? Ceph GPT wrote the outline for my talk. I'll give you an outline, introduction, background of Ceph at CERN, 10-year review of how it was to operate, and some lessons learned and future directions. Of course, the outline was more detailed than it gives. So I'll give a brief overview of our use, the importance of it in our infrastructure. This is real output from ChatGPT, guys. Unbelievable. And the purpose of this outlook. So here's the introduction. This is overview of Ceph at CERN. We started in 2013 with a 300 terabyte proof of concept that we tried to break. We couldn't break it. Okay, and then that allowed us to justify a 3 petabytes cluster back in 2013 for OpenStack. 2014, 2015, we did some R&D in erasure coding, writing the first ISA acceleration for erasure coding. We developed the first object striping for a particular use case that we had for physics data. 2016, we upgraded our in-place stuff from 3 petabytes to 6 petabytes. This was like proving that Ceph organic storage actually was really, really working. Then we had 8 production clusters. Then we got into Cephfs and S3 in production. Scaling out, okay, I run out of things. There's nothing so notable there in those years, but we're scaling out business continuity, disaster recovery solutions. By now, we have around 17 clusters and around 100 petabytes on the floor. This is interesting, these two numbers, because in 10 years, that's about 5 Moore's Law doubling periods. And that's almost exactly matching, right? That's like 96 petabytes if you do the math. That's kind of interesting. But it also means that my Ceph budget did not increase in 1 decade. Okay, importance of CERN and Ceph's infrastructure. Okay, this is just the logo drop. Boom, this is all the stuff. It runs the whole infrastructure at CERN, IT infrastructure, analytics platforms. We don't use Ceph for the massive scale. That 100 petabytes is within a context. It's within an exabyte context of disks and tapes for physics data, but we use it sort of for everything else. Okay, so it's really proven. It becomes the key piece. Purpose of this talk. If you don't remember your history, you're condemned to something. Decade's a round number, and I've got 10 fingers, so 10 sounds like an interesting number. And it's kind of like a memoir, you know. Okay, next section. Why did CERN choose Ceph as its storage solution? Challenges faced in implementing an overview of the Ceph architecture. Why Ceph? So going back, you know, we started with OpenStack. The management forgot to get a storage solution for the cloud, so okay. See what's out in their open source land. Ceph was the best. We tried Gluster, we tried our NetApps, we tried Ceph. Ceph was far and away the best. We all know that story. The key thing was we needed an organic system that would grow with our usage and our evolving use cases. Flexible storage, no data migrations. Data migration, like forget it. You can't just like shift the data to another platform as you're growing. So on the floor, behind the scenes, transparent migrations, that was key. And it has proven for 10 years, this is it, it works. Also, best bang for the buck. We wanted that Linux feeling, right? You buy the cheapest commodity hardware, and you just put some free software on top, and you get something enterprise quality. And it's true, it all works. This all ended up as true. Challenges implementing Ceph. So these are more like, let's say, the initial challenges. When you start, and this is, I think, probably echoed, many people have this thing. You want to install the software, you need to make it work on this hardware or else. The hardware comes from someone else decides which hardware. We buy it in bulk for scientific use cases, okay? And it's always 2 gigabytes per CPU core, always the largest, cheapest hard drives, data center hard drives, not desktop stuff, always in JBODs of 24 that you can then do 24, 48, up to 96, let's say. Why do you need 3 replicas? This is, people are still asking that question. Why do you need SSDs? This is still something to justify. There was also some not invented here syndrome at CERN. There's a storage department of 50 developers at CERN, so to use something from outside took quite some work. There's the impression that the only thing good about Ceph is Crush for some reason. Crush is even broken, right? Crush actually doesn't work. I'll get into that a little bit later, tiny bit. But the real value of Ceph is that engineering effort to make the failures transparent and the OSEs just heal. That's the real true gem of Ceph. And also, the old timers said, forget about any kind of software-defined storage. You'll never solve the latency problem. There'll always be 1 or 2 extra hops and just forget it. So that's kind of still true, isn't it? But anyway. Our architecture. So I'm just following ChatGPT's outline, right? This is not creativity at all. I'm so lazy. It's the same host recipe since the beginning. We have server quads. I've got a picture on the next slide. Dual Xeons, now AMDs. Always 2 gigabytes per hyper-threaded core. Now these are 256 gigabyte machines. Went from 1 gig to 10 gig to 25 gig on our standard stuff. We have 100 gig testing as well. Always dumb HPAs, never RAID controllers. 1 or 2 of those JBODs. And then always, I managed from the beginning to convince that we need a little bit of flash. It was a reliable file store journal at the beginning. And now it's Blue Store, block DBD, and WAL on the flash. Originally, we were spending a bit extra, 5 drive write per day SATA SSDs, 5 per OSC, 5 OSDs per. Now, scale down a bit. It's around those 1 drive write per day NVMEs, and totally comfortable running 12 or even more OSDs per NVMe. It's fine. Here's the photos. This is probably the same aisle, just to prove that nothing has changed. These are those server quads. They used to have, you've probably seen these. There's 4 servers in there, and then those 24 disk JBODs. It's the same. And that picture's even from 2017. I just got bored of taking pictures because it's always the same. Yeah. All right. Network-wise, very simple stuff. We originally, originally we had this idea that, okay, actually what it is, let's say at CERN, it's complicated to plan where you're going to get space in the data center, so the servers just end up anywhere. So then you try to make a cluster across like different switches, across different routers, multi-path routing, and we learned that this is not the way to go with Ceph, because any kind of fault anywhere and you've got OSDs flapping up and down, it's just a disaster. So now we usually put it all behind one switch, which is also slightly crazy. But if you have many clusters and you teach your users about trying to use many clusters, this probably ends up a more reliable system. So most of our issues are related to router line card failures or packet corruption. Now we just use sort of one cluster behind one switch. The whole cluster will go down, inaccessible, all at once. It's better, I think. We used to, it's better, yeah. Well, there we go. Something for after to discuss. We used to have one cluster for all. This was also the dream of Ceph, right? One cluster, you create a pool for all these different things. But we now have several clusters across several zones. Teach your builders about downtime budgets is like the most important thing. This is part of the Google SRE book, right? Downtime budgets. Spend your downtime budgets too. Okay, where are we on to now? Ceph GPT. I hope you noticed the Ceph logo on Ceph GPT. Yeah. Performance and scalability, upgrades, challenges, and success stories. So performance. Yeah, I guess I was a little bit tired when I wrote this slide. Ceph performance can be summed up like it is what it is, right? It's not performance first. In that triangle of things that you choose between consistency, availability, and performance, I mean, partition tolerance, but whatever. We prioritize consistency and availability in Ceph, or partition tolerance. It's actually a CP system, but anyway, we don't prioritize performance, right? That's Mark's job. Always keep Mark busy. But anyway, the users always expect like raw NVMe FIO performance. Like management will buy, okay, these things they say do 1 million IOPS, and I gave you 1,000 of them. Like, where's my billion IOPS? Right? That's the expectation. So always have to remind the complexities of distributed clustered storage across the network. But anyway, I think this isn't even a problem. In experience, 10 years, almost nobody understands their I/O workloads and requirements. Everybody wants that performance, but in practice, we still throttle our attached storage to 200 IOPS, 500 IOPS. We allow bursting up to 1,000. Everybody's happy. Almost like 99% of people are happy. So that's the scale-out storage performance. However, like from the operations side, there's still like, you really want this. It must be possible to take 100 petabytes of disks and put small amount of flash and make, the goal is, I want like a cheap performance fix. Make the cluster perform like 100 petabytes of flash transparently, and it should be just like invisible. FileStore had a simple way to speed up writes. This was nice. I think a lot of Ceph operators appreciated this. And then lots of clever folks used Bcache. I don't know if anybody in the room remember doing this kind of thing. We used Bcache. You still do, yeah. But it's scary to put other things in between. I think it's scary. Okay, I know it's probably working in practice, but it's scary to put other things because Ceph wants to scrub the disks and detect the durability issues immediately itself. BlueStar is deferring small writes to BlockDB, but I'm pretty sure it's still bottlenecking on fsyncs to spinning disks, so we don't quite get the same performance out of BlueStar as we did with FileStore for writes at least. But maybe it's a config issue. We're talking to Mark about this. I just know from other file systems that I use, like ZFS, they have a persistent layer 2 cache and log device, and it works very well to sort of hide that spinning disk slowness underneath. And it would I think we should try to put something more, focus on this a bit in Ceph, to put something more like that built in directly to Ceph, instead of having to rely on Bcache and other things. But there was one like cheap fix. This is actually a plot. It's unfortunate. I didn't have the I didn't look forward enough when we set up our original monitoring dashboards 10 years ago to set the storage schema to keep 10 years of retention. So we only keep 5 years of retention here. And this is a plot of the, like every minute on every Ceph cluster, I run Rados bench, 4 kilobyte writes, and just to see how long it takes to write the objects. And this is what this is on on our biggest, original, oldest cluster. And actually the laser doesn't work on this. You see it was originally it was under 10 milliseconds for this slow bulk stuff. It got pretty bad there for quite a few years. 2018, 2019, up in above 50 milliseconds for a 4K write. I mean, that's terrible, right? But what's interesting is that nobody complained. Because it's protected it's like inside a VM. Who does synchronous I/O like consciously? Almost nobody is. It's all buffered, and Linux is flushing it behind the scenes, and the users didn't even really notice. But then, okay, we got some AMD EPYC CPUs, and then nothing worked. It got like completely broken. Is anyone from AMD in the room? Okay, it wasn't AMD's fault. It turned out to be that you see around like end of 2021, like suddenly the latency went down, and it's because we learned that spinning disks around the like say 14 terabyte generation across manufacturers added what one of the vendors calls a media cache, and this thing specifically, I mean, I still haven't been able to dig out why they did it, like for exactly which use case. It must have been in collaboration with one of the enterprise NAS vendors, but specifically it accelerates synchronous direct I/O. So if you're using ODirect and OSync at the same time, like Ceph does, it accelerates it in a fast part of the disk. Okay, so it turns all of if you have it off on these latest generation drives, yeah, cool. Magic fix, yes. If you turn it, if you have the switch to turn this on and off is just to turn the write back cache on and off on the spinning disks, WC on, WC on off. Out of the box, they're usually coming with with that write cache on, and recent generation disks are just completely unusable. But you switch those disks to write through mode, and it's like magic fix mode. Your whole cluster becomes, with spinning disk, performs like almost like SSDs again. It's like, this is a spinning disk cluster, and that's really great. We still are like scared that something is not persisted, but that's a couple of years now. I mean, this looks too good to be true, right? Yeah, it looks like, that's what it looks like. But so far so good. Okay, scalability. So we had lots of fun with our Big Bang scale testing. We did a couple of blog posts with Sage on this. In 2015, we did a 30 petabyte test when that was a big number. Then in 2018, we did a 72 petabyte Ceph test with over 10,000 OSDs, because Ceph actually has a not hard-coded, but a maximum 10,000 OSDs per cluster. And we just wanted to have a test where we could bump it up above that. We did that, and we found lots of problems. I mean, all of the maps were too large. The cluster was flapping up and down, OSDs flapping. The Mon was completely overloaded with getting all the PG stats and everything. It was just way too noisy. So clusters were really inoperable above 2,000 OSDs. That's why we have the Ceph manager now. That's the reason. We spun off Ceph. All that work was going to the Mon in the past. We moved all the non-critical workload over to the Ceph manager daemon, and then also gave as a bonus people that like are Python devs and things like this. It gives them an easy way to contribute to Ceph through the modular interfaces of the manager. But still, I think we should avoid putting more than a few thousand. 2,000 to 3,000 is about the limit. Although afterwards it gets sluggish. I don't know, I see Andras is. Yeah, you see some things, yeah, exactly. Yep, okay, some improvements. BlueStore was a huge improvement. File store was convenient, simple to understand. There were a lot of painful things, like splitting the directories and then merging them back. I mean, this was quite painful. People these days can just ignore that. You have a nice, warm, fuzzy feeling from BlueStore that it's always serving good data. You didn't have that with FileStore. End-to-end checksums now with BlueStore. Someone's shaking their head no. Yeah, someone's shaking their heads, yes, okay. Well, jury's still out on that. I've got that warm, fuzzy feeling. But it is pretty scary. One of my managers said, because he was like, oh, I remember Oracle did the same thing, invented their own file system underneath. And it took like, I don't know what he said, that's before my time, but he said it took like decades before that stabilized. Maybe someone else knows. There are still some, BlueStar is still scary. But this like major kudos to those low-level gurus that know how this works and know how to FSCK a corrupted BlueStar. Wow, that's a place we can improve. Most cluster operations are more civilized. I've got some stuff on the next slide. Cephfs, this is improvements of both Ceph over the time. Cephfs was, remember, in the olden days we had Ceph is like this is awesome, block store is awesome, object store is awesome. Cephfs was almost awesome for the longest time. And then it was declared awesome, right? And it continues to improve today. Some of the challenges operating Ceph, we learned early on, and we still know to like make changes gently to a Ceph cluster. Don't do like massive. I think in Berlin I had to talk about leap of faith. Like sometimes you do a Ceph command and then, oops, see you in like 3 months. In a large cluster, rebalancing is the normal state of a cluster. So kind of like tuning that, understanding that, feeling the heartbeat of the cluster is important. We aim in our operations to aim for a health okay with no backfilling at least once a week. If you're doing things if you keep doing operations that take weeks on weeks on weeks, I mean, things will accumulate and you'll be in trouble. I'm sorry. We have some scripts to do this. Gentle rewrite, gentle split. These used to be really used. I don't know how much people use them anymore. But Ceph is getting really good at this now. It's solving most of these kind of operations problems. Now it has, it tracks the number of misplaced objects. It keeps that all within a scope. It has schedules for the balancer and scrubbing and stuff. It's all of this got much better. But I think it's still way too easy to do that. Oops. I don't know, a couple of months ago, someone was on the mailing list. I don't know if they're in this room, but I did this, and then it was just like, really, we estimate it's going to take 3 months to complete. Jeepers. I can't imagine. That's a long time with no sleep. I think we should do something like Nomad and Terraform, where you can type a change, plan it, it'll tell you what it's going to do and how long it should take, and then you can apply it. I don't know, something like that. That kind of semantic would be really helpful for operators. Other challenges, remember when non-uniform data placement was like costing us all a lot of money? Unbalanced OSDs, if you had a 10% variance, this would cost millions, right, in lost space, petabytes. UpMap Balancer solves this problem, problem solved. But because, and this is what I alluded to earlier, Crush is broken. There's some mailing list threads. If you have the same size everything, it's fine, but as soon as you have some different sizes, actually the algorithm's wrong, I'm sorry. There's threads about this, it's called the multi-pick anomaly and stuff. Maybe somebody smart wants to fix this one day, but it would require some deep work. The built-in balancer is really great, but it's not perfect in all systems. This is where power of the community, the JJ. Are you here, the JJ? That's you? Oh, yeah, people use it. This is great. So it works really well. And this UpMap tool is really a Swiss Army knife of for like more experienced Ceph operators. This is a kind of mechanism we can use to direct data exactly where we want. And there's PG Remapper from I think DigitalOcean, right? And UpMap Remap that we made. I mean, these kind of things are quite useful. These are features we want to bring into Ceph somehow. Scaling Cephfs remains probably the more challenging out of the Ceph daemons because the MDS is single-threaded, so you need many of them. It's very stable these days. It's very stable, but like adding, removing on the fly, this is not so practical. If you've got like some AI workloads running there and you need to upgrade, and it's hard to convince like 1,000 physicists that we're going to do an upgrade and they have to stop all their long-running, month-long jobs. So there's a bit more, and it's still scary if there's a problem in Cephfs. This remains a very scary thing, and snapshots are a bit too scary to enable at scale. And I wrote Ask AP. I mean, I think there's somebody in the room here that might have a tear in their eye thinking about Cephfs snapshots. S3, scaling one region is not very hard. We had trouble with, our stack is Trafic front ends. It used to be HA proxy. We switched to Trafic because we manage it all with Nomad. And we route, Rados gateway speed performance comes from spreading across many buckets, spreading across many Rados gateways, but we group our Rados gateways using pattern matching on the bucket names according to our different user communities. This is a good way to get nice performance. We suffered some issues, but it's overall working very well. But multi-region seems difficult. I heard maybe it's going to be fixed in Quincy or Reef. It's getting there, so we'll see. I'd like to hear more about that. It makes it easy. I alluded to this earlier. It makes it too easy. Ceph makes it easy to put all your eggs in one basket. But someone told me don't put all your eggs in one basket. We learned the hard way. I don't know if someone can. I don't know if the slides will be available afterwards. But if you're curious, in February 2020, we made a talk. This is from June that year while we were all in lockdown. But this was a talk that was called like the bug of the year. Okay. Actually, little did we know that there was a bug of the century at the same time that we were there fixing, just emerging, right? But what happened in this, that there was a bug in the low-level LZ4 compression library, and it just corrupted all the OST maps on all the OSTs at the same time. And I was having a coffee, and then boom. I had to put it down, and then that was an 8-hour, very painful, traumatic day. But everything recovered perfectly. All the data was intact, not one single bit lost. And now Ceph is stronger because of it. But this motivated us to spread out across many clusters and learn about, storage availability zones and things like that. And
was that the day your IO dropped to nothing?
Oh shit, I gotta go. No. Successes. I didn't want to put all the successes because there's just too many, but I wanted to talk about why it succeeds, right? It succeeds because it integrates with the platforms. This always is we can't forget this. You got to stay trendy, like Sage used to say. It was Kubernetes, it was OpenStack, now it's Kubernetes and OpenShift and the CSI stuff, and then CephFS and S3 make it integrate with everything. That's why everything you can download, anyone downloads something from GitHub, it's got an S3 backend, right? That's why we're even here probably now. It succeeds because it protects our data despite faults everywhere. Someone's going like this? I mean, no, come on, it goes. It does. We didn't have any corruptions. 10 years, no corruptions. It's like a core building block, thousands of apps trusting it, at least in our environment. It continues to grow, continues to be flexible, expanded. I think we've been through 4 hardware generations with the same bits. Yeah. And the user community, it's always been the strength of Ceph. Let's not forget, it built up because of all of these Ceph days, the community manager over there on his phone. Oh, taking a picture, that's why. Yeah. COVID hurt us, really. The community is kind of like, we're not doing the best. This is the best thing to happen in a few years now. So, and I hope to see everyone at Amsterdam as well, because a good community is good for all of us. Okay, whoa, this is a pretty long, outline. I'm probably out of time. Lessons learned and future directions. Key takeaways from 10 years of operating Ceph at CERN. All right, so I couldn't. What were my key takeaways from running Ceph at CERN the past 10 years? Here we go. Okay. Proper planning and design. This is real, guys. It's terrifying. Proper planning and design are critical. You can read this later. It's hilarious. Monitoring and maintenance are essential. Resilience is key. Testing is crucial, and collaboration is important. Running Ceph at scale is a complex task. It's important to collaborate with other organizations and individuals who have experience. This includes participating in the open source community, attending conferences and meetups, and sharing best practices with other Ceph users. Oh man. So yeah, I just wanted to thank my brilliant CERN colleagues who helped build our IT and storage infrastructure, to the kind and knowledgeable community, the hosts today and those that helped organize it, and of course the giants who build Ceph, standing on your shoulders, really. That's the end of my talk. Thank you.
Come on, questions.
Great talk, thank you. Two quick questions. 5 years of retention for you is like 25 for the rest of us. I'm pretty sure I'm speaking for everybody here.
Okay.
So congrats on keeping all that data there. But how many operators do you actually have running this back end, like managing this on a day-to-day basis?
2 warm bodies.
24/7, just on call?
Oh,
Or just
no. I mean, so no. I mean, so CERN has we have our data center. It's old school. We're building a new data center. There's one person that sits there all the time just looking for things to turn red, who then calls a list of the phone. Okay, that's the database. They call that, on call type stuff. The Ceph team is two people, basically 2 warm bodies, maybe with a couple of students, maybe. Yeah. But that's part of a storage team, which is like 40 or 50 people doing all kinds of things, which is part of an IT department with 250 people, right? You don't need many people if you're focusing on one technology, right? Great. Thank you.